remain the same. So no matter how many packets you have in that flow, you could have a million packets to download the movie, but those three values will remain the same, and every packet will hit the same location in that space. So you will get a single dot for a legitimate flow. But for attack flows, they change one or two fields from packet to packet. Okay, every packet has one or two values different. Okay, so they sort of move in that space and generate this geometric shapes. Okay, so doesn't really. I mean, it's not that the legitimate flows is really small in quantity in terms of the number of packets. It's just that the attack flows sort of inflate themselves and manifest themselves in this space. Okay, and that's a good news to us. Okay. Okay, so far we have seen this visualization idea. So it seems to be cute, but the question here is that does that visualization method inspire any novel approach to detecting attacks? Actually, you can see that figure here after it happened, but can it draw the picture in real time? The answer is probably not. Especially if you have a thick pipe like OC192, for every arriving packet, if you want to draw a dot, that's out of the question. Okay? That's one problem with that visualization when we want to use that for the real attack detection software. The second and more fundamental problem is that it can hide some low intensity attacks and the attacks in the close proximity of the legitimate traffic cloud. Okay, if it is hiding there, then you cannot see it. Okay, but there's an idea that we can actually draw from that visualization stuff, and it turns out that the idea can in fact not only visualize, but it can detect and classify and measure the intensity of those attacks. And it can be done quite fast, so it can run on high-speed links and in real time. So in the second part of the talk, we'll briefly look at that. Well, the idea is that the only attacks appear as a regular geometric entity in that 3D space. And they sort of exhibit this sort of quote-unquote pivoting behavior. Of the three values, they fix one or two and then move the others. Okay? So one of those three values, there are things that move. Okay, the coordinates that move. So we can detect that pivoting patterns and sort of exploit that property to get only the attacks, okay, while ignoring the legitimate traffic. So how do we pan out this pivoting behavior? First, let us define a flow to be a three-tuple consisting of source IP address, destination IP address, and destination port. And then we define the signature for a packet, and the signature corresponds to the flow three-tuple. But the values here will be binary. So KS, KD, and KP, they're all binary. And the binary values tell you whether or not you saw the corresponding value in the flow three-tuple recently. Okay? If you saw the value recently, for instance, if you saw a particular destination IP address recently, then you generate 1. Okay? If not, if you don't remember seeing that value, then you generate 0. Okay? And the question is, how recent is recent? We'll talk about that later on. But basically the idea is that if you see a 0 in a packet's signature, that's where the movement is on. Okay? So you want to catch the movement, right? Because if dots move, that draws a line, that draws a rectangle, and so on. So you want to catch the movement. So okay, basically this is how the signature is generated. Suppose you got a flow at time t, and source IP address was 3456, and the destination IP was 5678, and the destination port number was 90. Let's call that flow 1. And at time t plus 1, you see another flow, basically a packet, but packet has this flow information. So 1, 2, 3, 4 is SIP, 5, 6, 7, 8 is DIP, 80 is DP. And at t plus 2, you get 1, 2, 3, 4, 3, 4, 5, 6, and 90. So what signature do you give to the third packet? Well, you give 101 because you saw 1, 2, 3, 4 in the SIP position before. Suppose your memory is 2 time units. Okay, it spans 2 time units. So you remember flow 1 and 2. But 3, 4, 5, 6 in DIP position, you don't remember seeing it in the previous 2 packets or flows. 90, you saw it. Okay, so it gets 101, and that's what you get as a signature for this packet. And once you do that, you can define your attack signatures. Okay, for instance, if you have host scan, it's 101. Okay, you see this. You keep seeing this source IP address. Okay, and you also keep seeing the destination port, this particular port number. But you see in the same packet, you see differing destination IP addresses. Then you will keep generating this signature for the arriving packets. What about DOS? Well, since they are usually, the source IP addresses are usually spoofed, you will see new source IP addresses, but you will keep seeing this IP addresses, which is the victims. And if destination port is fixed, then you will see the same port number quite frequently. Okay, so like this, you can define the attack signatures. We can talk about it for quite a long time, but I guess we'll stop at that. So you have the attack signatures. One of the attack signatures that is interesting here is what we call Kamikaze. That's 100. And actually we see this strange type of attack in our trace. It was too fast for you to see, but at 512 to 515, you can see actually this rectangle here. Okay, it has the same source IP address, but varying destination IP and varying destination ports. What does this mean? A single source is spewing out packets to so many destinations and to so many ports. Why is it doing that? It doesn't make sense. It's only suicidal, right? It's spewing out, but it's not. It cannot be an attack to anybody. Well, a plausible explanation is that it's a backscatter from a DOS victim. Okay? A source spoof DOS is hitting this poor guy, and he's responding to it. Okay? So it looks like it's spewing a lot of packets to this entire destination IP space. Okay. So we have this attack signature, and how do we implement this in our software? Well, basically we use hash tables. So for source position and destination IP position and destination port position, we have separate hash tables. So when a packet passes, it reads in the appropriate fields, and these hash tables will generate 1 or 0, and combined they will constitute a single signature. When signature is generated, depending on what kind of signature, okay, we have a table here, right? Depending